Good morning, my dear students. This is Dr. A.V. Parakusam, Professor in Department of ECE, Lendi Institute of Engineering and Technology. I have taught signals and systems and communication subjects for GATE students for last 10 years in various GATE coaching centers like Vani Institute and GATE Forum. In this lecture, I will explain Laplace transform. What is ROC, region of convergence, that is related to the Laplace transform, and relationship between Laplace transform and Fourier transform, poles and zeros, and inverse Laplace transforms. I will cover these 5 topics in this lecture. After completing these 5 topics, I will solve one problem which is given in GATE 2015. Here, I start the lecture with the definition of Laplace transform. Suppose a signal x of t is there, the Laplace transform of signal x of t, is represented by x of s is equal to integration minus infinity to plus infinity, x of t into e to the power of minus st dt, So this is the definition of Laplace transform of a signal. Okay. What is s? S is a complex variable. Which is equal to sigma plus j omega. Where sigma is the real axis and j omega is the imaginary axis. Here I draw the s plane. This is sigma, real axis, and this j omega is the imaginary axis. This is the s plane. Okay. So this is about s plane. Now we see the relationship between Laplace transform and Fourier transform. So this is the definition of Laplace transform now. What is S? S is equal to sigma plus j omega. Now you substitute this sigma plus j omega in this definition of x of s. Then this is equal to integration minus infinity to plus infinity x of t into e to the power of minus sigma plus j omega t dt. This is equal to integration minus infinity to plus infinity x of t into e to the power of minus sigma t into e to the power of minus j omega t dt. Okay. Now you put x of t into e to the power of minus sigma t in bracket. Now this is the definition of Fourier transform of x of t into e to the power of minus sigma t. This is the definition of Fourier transform of x of t into e to the power of minus sigma t. So after arriving to this result, we can conclude that Laplace transform of x of t is equal to Fourier transform of x of t into e to the power of minus sigma t. Fourier transform of x of t into e to the power of minus sigma t. What is the meaning of this one? Suppose x of t is given. I want to find a Laplace transform of x of t. How do you find? The simple technique is that you take that signal x of t, you multiply that x of t with decaying exponential e to the power of minus sigma t. After getting the result of that x of t multiplied with e to the power of minus sigma t, now you find the Fourier transform for that signal. That is the Laplace transform. From this result, one more point we can derive. That point is that suppose sigma is equal to 0. sigma is equal to 0. What happens to this relation? What happens to this relation? The Laplace transform of x of t is equal to Laplace transform of x of t is equal to Fourier transform of x of t into e to the power of 0, because sigma is equal to 0, no? E to the power of 0, that is equal to e power 0 is equal to 1. Fourier transform of x of t. See, we have reached one important relation, that is the Laplace transform of a signal is equal to Fourier transform of that signal. Under which condition? When sigma is equal to 0. Sigma is equal to 0 means you in the S plane, can you identify where sigma is equal to 0? This is S plane. This is S plane. This is sigma. This is j omega. Where sigma is equal to 0? This j omega axis. This j omega axis. On the j omega axis, sigma is equal to 0. So, on the j omega axis, the Fourier transform is equal to Laplace transform. The Fourier transform is equal to Laplace transform. So, this is an important result that we have obtained by setting sigma is equal to 0. Okay? So, this is the relationship between Laplace transform and Fourier transform. On the j omega axis, the Fourier transform, the Laplace transform will be equal to the Fourier transform of a signal. Okay, now we discuss about region of convergence. Region of convergence. What is region of convergence? ROC. The region of convergence is nothing but the values of S for which the Laplace transform is existing. That is called region of convergence. For example, I take a signal e to the power of minus at e of t. E to the power of minus at e of t. For this signal, the Fourier transform is existing. For this signal, the Fourier transform is existing. I take another signal e to the power of minus at u of minus t. For this signal, the Fourier transform does not exist. The Fourier transform does not exist. Whereas for this signal, the Fourier transform will be existing. The Fourier transform will be existing. I take another signal e to the power of minus at into e of e to the power of at into e of t. Let us take another signal also, e to the power of at e of minus t. So, how many combinations? 4 combinations. With by using e to the power of minus at, e to the power of at, e of t and e of minus t. 4 possible combinations. For this signal, the Fourier transform is existing. For this signal, the Fourier transform does not exist. For this signal, the Fourier transform does not exist. For this signal, the Fourier transform is existing. The Fourier transform is existing. Okay? Coming to the Laplace transform, for all these signals, the Laplace transform is existing. For all these signals, the Laplace transform is existing. Here, the Fourier transform does not exist for some signals and it exists for some other signals. But Fourier Laplace transform is existing for all the signals, but with some conditions. What are those conditions? That conditions are given by the region of convergence. Region of convergence. That is, the Laplace transform is existing whether the Fourier transform will be existing or may not exist for that signal. That doesn't matter. But Laplace transform is existing for all classes of signals, but at some values of S only. That values of S are given by the region of convergence. That values of S are given by the region of convergence. Let us discuss why the Fourier transform exists for some signals and the Fourier transform does not exist for other signals. Let us see. Here I draw the e to the power of minus at e of t signal. E to the power of minus at e of t signal. Assume that for all these signals, A is greater than 0. A is positive. A is greater than 0. Assume that For all these signals, a is greater than 0. E to the power of minus 80. Actually, e to the power of minus 80 is a decaying exponential. E to the power of minus 80 is a decaying exponential. This is e to the power of minus 80. At t is equal to 0, its value is equal to 1. But here we need to draw the e to the power of minus 80 into e of t, no? What is e of t? E of t is a signal. E of t is a signal whose value is equal to either 0 or 1. When its value is equal to 0, when t is less than 0. When its value is equal to 1, when t is greater than or equal to 0. Similarly, e of minus t. What is e of minus t? E of minus t is also equal to 0 or 1. Is also equal to 0 or 1. When its value is equal to 0, when t is greater than 0 and t is less than or equal to 0. See here, e to the power of minus 80 is multiplied with e of t. E of t is equal to 0 when t less than 0. So then this value becomes vanish. Is equal to 0. So the value is equal to 0 for t less than 0 and for t greater than 0, it is same as e to the power of minus 80. So this is the signal of e to the power of minus 80 e of t. Here I draw the e to the power of minus 80 e of t. E to the power of minus 80 e of minus t. E to the power of minus 80 e of minus t. We know the graph of e to the power of minus 80. It is a decaying exponential. But this signal is multiplied with e of minus t. What is e of minus t? It is equal to 0 for t greater than 0. For t greater than 0. Okay. For t less than 0, it is equal to 1. E of minus t is equal to 1. Okay. Next. Here I draw the e to the power of 80 e of t. What is e to the power of 80? It is increasing exponential. It is increasing exponential. But e to the power of 80 is multiplied with e of t, no? Then its value becomes 0 when t less than 0 and it's existing for t greater than 0. What is e to the power of 80 e of minus t? Again you draw the e to the power of 80. E to the power of 80 at t is equal to 0, 1. Okay. It is multiplied with e of minus t, no? So it becomes 0 when t is greater than 0. So now these are the signals. These are the signals. So one condition is that for any signal x of t, the Fourier transform exists if that signal is absolutely integrable. That signal is absolutely integrable. Suppose x of t is there. The Fourier transform for this x of t is existing if it is absolutely integrable. Absolutely integrable means you take the integration for that signal from minus infinity to plus infinity and you integrate that signal by taking the absolute value x of t dt. This value should be less than infinity. Should be less than infinity. Should be less than infinity. Then the Fourier transform is existing. Then the Fourier transform is existing. This is the condition. This is the condition. So, of course, it is not necessary here to integrate all the signals, whether that value is less than infinity or not. By seeing those signals, we can come to the conclusion that signal is absolutely integrable or not. See here. Here the signal as t tends to infinity, the signal tends to 0. So this signal is absolutely integrable. Absolutely integrable. Now coming to this signal. This signal as t tends to minus infinity, this signal tends to infinity. So this is not absolutely integrable. Absolutely integrable. If you integrate this signal from minus infinity to plus infinity, definitely you will get infinity value. Here, if you integrate the signal from minus infinity to plus infinity, definitely you will get a finite value, not infinite value. Of course, that finite value is equal to 1 by a. 1 by a. And here also, it is not absolutely integrable. Not absolutely integrable. Because as t tends to infinity, it increases. It is a divergent function. It is convergent function and it is also convergent function. These two are divergent functions. And here, as t tends to minus infinity, it tends to 0. It tends to 0. So it is absolutely integrable. Absolutely integrable. Absolutely integrable. So now can you tell me for which signals the Fourier transform exists, and for what signals the Fourier transform does not exist? You can easily tell that this signal the Fourier transform is existing. For this signal Fourier transform is existing. For this signal the Fourier transform does not exist. For this signal the Fourier transform does not exist. For this signal, the Fourier transform is existing. The Fourier transform is existing. Here, the simple idea is that how do you come to the conclusion whether the Fourier transform is existing or not? You just have a look on this expression. Have a look on this expression. E to the power of minus at e of t. E to the power of minus at e of t. Here e of t is there. Because of this e of t, this signal is right-sided signal. Because of this E of t, this signal is right-sided signal. If it is E of t is there, if E of t is there, this is shortcut. This is shortcut. If E of t is there, it is right-sided signal. You just observe what is the coefficient of t. What is the coefficient of t? That is negative. Negative. Okay. Similarly, for this e to the power of minus at e of minus t. This is e of minus t is there. Because of this e of minus t, it is left-sided signal. It is a left-sided signal. And you observe the coefficient of t. It is negative. Negative. And here, this is right-sided signal. This is positive. This is also left-sided signal. This is positive. See, for right-sided signal, if the coefficient of t is negative, then the Fourier transform exists. For right-sided signal, the coefficient is negative, the Fourier transform is existing. Okay. Next, where is the right-sided signal? This is also right-sided signal, but the coefficient is positive. So the Fourier transform does not exist. Next, for left-sided signals. For left-sided signal, if the coefficient is positive, the Fourier transform is existing. For left-sided signal, the coefficient is positive, then the Fourier transform is existing. Here, this is also left-sided signal, the coefficient is negative, so the Fourier transform does not exist. So you keep these 2 points in your mind. For right-sided signals, if the coefficient of in the exponential term, if the coefficient of t is negative for right-sided signal, the Fourier transform is existing. Otherwise, Fourier transform does not exist. That is one point. The second point is that for left-sided signal, the coefficient of t is positive, then the Fourier transform exists. Otherwise, it does not exist. Now we come to the reason of convergence after having this knowledge.